Hello, and welcome to our program, Astronomy for Everyone. The topic for this month's program is the DART mission. And here to tell us all about it is our guest, Jeff Woytach from NASA. Jeff, welcome to the program.
Thank you, Don. Thanks for having me. It's a pleasure to be here for everyone. I'm Jeff Woytach. I'm a lead systems engineer at the NASA Glenn Research Center in Cleveland, Ohio. I've been with NASA for just over 39 years. I've worked on missions that we've launched on the space shuttle, hardware that we've launched to the International Space Station, worked on spacecraft that we launched on Atlas Centaur launch vehicles as well. I'm currently the lead engineer for the next generation radioisotope thermoelectric generator project for the agency, which will be producing essentially a nuclear battery for the future of deep space exploration. And as Don said, we're here tonight to talk about one of NASA's most recent, most interesting missions, almost something right out of science fiction, the DART mission.
Now, Jeff, what does DART stand for?
Well, DART stands for the Double Asteroid Redirection Test. It's a mission that was testing ways of actually combating potential asteroids that are hazardous to the Earth, and testing a way that we could actually deflect an asteroid that might be on a collision course with the Earth.
All right, well, why was this mission developed? You alluded to it right there, any potential hazardous asteroids heading our way.
Yes, as a matter of fact, it's more than most people may realize that jeopardize the planet. We are a target because our solar system is not a clean place. We look up in the night sky, we see the stars, we see the planets, but we don't see the leftovers of creation, the pieces of flotsam and jetsam that we call asteroids and comets that are in the solar system, that are the leftovers of planetary formation. These are the debris left over from the dust cloud from which the solar system, the sun and the solar system formed many billions of years ago. And they are all through the solar system. We saw an example of one of these in 2013 over Chelyabinsk, Russia. It was an asteroid fragment, very small, about 20 meters in diameter, that weighed about 12 to 13,000 metric tons. So a metric ton is 1,000 kilograms. That's 2,200 pounds. So we're talking almost 30,000 pounds entering the Earth's atmosphere at 19 kilometers per second, well over 10 miles per second. And it basically exploded in the upper atmosphere with a force equivalent to 500,000 tons of dynamite. It didn't hit the Earth, but the explosion damaged over 7,000 buildings, and the resulting impacts brought injury to over 1,500 people. And there's evidence on the Earth of other impacts in the past. The Tunguska event in 1908 was an explosion attributed to a stony meteorite exploding over an area that flattened over 800 square miles of forest. Of course, the most famous is the Chicxulub crater off the Yucatan Peninsula in Mexico. It's believed to have been created when a large asteroid about 6 miles across actually impacted the Earth and caused the mass extinction of about 75% of life on the planet. It's believed that this is what is responsible for the extinction of the dinosaurs and, of course, the advent then of mammals. So we essentially owe our existence to the fact that this asteroid impacted the planet. If we look in Germany, we see the city of Rees, which exists inside an impact crater, an object that is believed to have hit at about 20 kilometers per second or 45,000 miles an hour, with a power almost 2 million times greater than the atomic bombs used in World War II. Now, we tend not to see a lot of these impact craters on the Earth because Earth has an atmosphere. So these craters erode over time. But of course, if we want to see evidence of impacts, all we have to do is look at our moon. All we have to do is look at the surface of Mercury, and they're covered with impact craters. So all through the solar system, this is happening. This is a diagram that's a number of years old now, but it shows the orbits of potentially hazardous asteroids that cross the orbit of the Earth. There's over 1,400 of them that were being tracked as of that time. So NASA developed a planetary defense office to actually undertake the task of tracking and cataloging these potentially hazardous objects that approach the planet. So over 20 years of observations, nearly almost 20,000 near-Earth asteroids have been discovered. Almost 900 of those are bigger than a half a mile in size. Over 9,000 of them are bigger than about 300, 400 feet in size. In fact, in 2018, 73 of these passed closer to the Earth than the orbit of the moon. And at least 5 times a year, a small asteroid impacts the Earth and releases greater than a kiloton of energy. Now, you may ask, well, why don't we realize this? Well, that's because over 70% of the Earth's surface is covered with water, with oceans. So that's where the majority of those actually come down. But all of these are being tracked by the Planetary Defense Office. We know the damage these can do, depending on their size, of course. And there are a number of theories of how we can actually protect the planet from the resulting impact. And one of the ways is being able to deflect an asteroid if we detect it far enough away from the Earth where we can change its orbit so it is no longer in danger of impacting the Earth. It sounds like something right out of science fiction, but it is truly something out of science fact. So that was the basis behind the DART mission, which was NASA's first planetary defense mission. As I said, it stands for the Double Asteroid Redirection Test. The DART mission, the spacecraft design, the operations of it were under contract to the Johns Hopkins University's Applied Physics Laboratory in Laurel, Maryland. They were the ones who also executed the Pluto New Horizons mission for NASA a number of years ago, where we had the first spacecraft do a flyby of Pluto and give us all those fantastic images of Pluto, Charon, and the other moons of Pluto. DART was targeted to an Earth-approaching asteroid called Didymos. Didymos was discovered in 1996. It wasn't realized that this was actually a binary asteroid until 2003. Images from the Arecibo Radio Observatory in Puerto Rico actually discovered that it had another smaller asteroid in orbit around it. And that asteroid was later named Dimorphos. Didymos orbits between the distance of the Earth and about 2.5 times the distance of the Earth from the Sun. So a year for it is 2 years and 1 month on the Earth. It has a very eccentric orbit, as you can judge by the difference in distances. The small asteroid, Dimorphos, is very small indeed. It's only about 170 feet across, and it orbits very close to Didymos. In fact, it only orbits about 1.5 miles above the surface of Didymos. And it orbited that asteroid about once every 12 hours, about 11 hours and 55 minutes. So that small moonlet was the target of the DART mission, to see if the kinetic energy of the impact of this spacecraft could actually alter the orbit of it around Didymos. If it could, then by impacting an asteroid, we know we could change its orbit. The DART mission was launched in early 2021, and it impacted Dimorphos in September of this year. These are some of the Arecibo radial images of Didymus and Dimorphos. Remember, this is radar imagery that has been translated into a visual image. So this was the first indications that we had of the Dimorphos asteroid in orbit around Didymus. It was chosen because it is an Earth-approaching asteroid, but it is not in danger of impacting the Earth. Also, the mass of these, even something that is relatively small as Dimorphos, still weighs hundreds of billions of tons. And the spacecraft at impact weighed about 1,200 pounds. So it would impact a substantial amount of kinetic energy, but not enough to ever completely throw it out of its orbit around Didymus and actually cause it to be a hazard to the Earth. So it was a great testing point for this kinetic impact theory. As I mentioned, prior to the impact, the orbit of Dimorphos around Didymus was about 11 hours and 55 minutes. Two were separated by 1/2 to 3/4 of a mile apart. Well, the DART spacecraft was targeted to slam into Dimorphos head-on in its orbit. And in doing this, it would actually slow Dimorphos slightly. And this is where orbit mechanics can get a little confusing. Because when you slow an object in its orbit around another body, that allows gravity to pull it closer. And as it pulls it closer, it actually goes faster. So in order to reduce the orbital period of Dimorphos around Didymus, in other words, to make it go faster, you actually have to impact it to slow it down. So gravity can pull it in and then increase its speed, and that is exactly what happened. So I think right now, Don, we'll turn it back over to you. We're about midway through the presentation, and after the break here, we can talk about the spacecraft itself.
That sounds very interesting, Jeff. We'll take a short break. If you have a question, please send us an email. The address is down at the bottom of your screen. And coming up next is Term of the Month with Stephen. We'll be right back.
Thanks, Don. The term of the month is aerogel. There is a fairly easy way to collect meteorites on Earth. Tiny meteorites, smaller than a millimeter across, are slowed by Earth's atmosphere and fall gently to the ground. They can be picked up and sorted from the debris collected by a backyard patio. The speeds are high in space, and when these small objects hit a spacecraft, they vaporize, and there's nothing left to see. So how could such objects be collected in space? Several space missions have used aerogel to do this. Famously, the Stardust mission had a collector with aerogel blocks. The collector was returned to Earth for study in 2006. Aerogel experiments have been recovered on shuttle flights, Spacelab 2, and Eureka missions. When a high-speed particle hits aerogel, it creates a cone-shaped track. The cone is largest at the entry point, here on the right, and narrowest where the particle comes to a stop. The particle can be extracted from just after the tip. Particle direction comes from the cone. When the Stardust mission was near a comet, the track indicated if it came from a comet or came from elsewhere at high speed. Silica aerogels used for these space missions are very low density and are surprisingly strong solids. The brick shown here is over 1,000 times heavier than the aerogel that is supporting it. Some 97% of the volume is comprised of very small spaces with a bit of air trapped in them. The remaining 3% is made up of three-dimensional intertwined clusters of silica. And that is the term of the month, aerogel. Back to you, Don.
Thanks, Stephen. We're back. We're here talking about the DART mission, and here to tell us all about it, continuing on, is Jeff Woytach. Now, Jeff, what can you tell us about the spacecraft?
Well, Don, as I mentioned earlier, the spacecraft was done for NASA by Johns Hopkins University's Applied Physics Laboratory in Laurel, Maryland. Well, as you said, Don, and as I mentioned earlier, the DART mission, the Double Asteroid Redirection Test, was done by Johns Hopkins University's Applied Physics Lab in Laurel, Maryland, for NASA. Um, the spacecraft was designed and built by them at their facility in Maryland. Was not a very big spacecraft, about 6 feet wide, 6 feet tall, and had two very large solar arrays that were actually technology demonstrations for deep space missions. They were roll-out solar arrays. When deployed, they were about 30 feet long, each one, and that was done to create power for the spacecraft and also create power for a low-thrust ion engine called NEXT-C, which stands for the NASA Experimental Xenon Thruster Commercial. Was built by Aerojet Rocketdyne based off a design for an engine that was actually created at the NASA Glenn Research Center in Cleveland, Ohio. Here are some images of drawings of the spacecraft that show that engine on its gimbal on top of the spacecraft, the rollout solar arrays in their stowed position, the Draco camera, which was a large telescope which helped to find Dimorphos and separate it from Didymus and helped target the spacecraft toward its impact trajectory. And this is showing the spacecraft with those solar arrays deployed. At launch, it weighed a little over 1,300 pounds, and at impact, after consuming its fuel, weighed about 1,260 pounds. The ion engine was a technology demonstration in addition to the arrays, and it did perform its mission very well, actually helping the spacecraft get to Dimorphos a little bit quicker than if Isaac Newton alone was in the driver's seat. However, it was not required for the mission. It had hydrazine propulsion system to perform that mission. It launched on a Falcon 9 launch vehicle, which had enough power to launch it directly toward the asteroid. These are images of the spacecraft itself during assembly at the Applied Physics Lab. The top left, you see the interior portions of the spacecraft bus, the communications antenna on the left. On the top, you see the ion engine, which actually had a protective cover on it for launch. The bottom right, you can see that engine itself on top of the gimbal. So when the spacecraft was launched on the Falcon 9, it was essentially upside down on the Falcon 9. The front of the spacecraft was actually facing downward. That is where the Draco telescope was. That also protected the telescope from any contamination that might happen during launch as well. But of course, DART's primary mission was to target and impact Dimorphos. As part of its guidance, navigation, and control, the team at APL developed the SmartNav system, small body maneuvering and autonomous real-time navigation. It would use the optical navigation system to identify and distinguish between Didymus and Dimorphos, and then working with the other guidance and navigation elements on the spacecraft, make sure the spacecraft targeted the correct body. This was based on many, many decades of work that had been done at APL on missile guidance algorithms, and the system worked very well. The optical input for this targeting system came from the Draco system, the Didymus Reconnaissance and Asteroid Camera for optical navigation. It was a high-resolution imager, had about a 20-centimeter aperture and a field of view of about 1/3 of a degree, using a high-resolution imaging detector, and was used to acquire the asteroid and fed information to the spacecraft so it could steer itself to a target on the asteroid. The telescope is also responsible for beaming back the images of the asteroids as it got closer and closer to Didymus and Dimorphos. Remember, Dimorphos orbited Didymus at a range of only about 1/2 to 3/4 of a mile away from it. So from a distance, it was almost impossible to distinguish those two. In fact, the final targeting of Dimorphos was only accomplished about 1 hour before the actual impact. The fact that we could target an asteroid like this at such a distance and impact it squarely center was an absolutely amazing accomplishment. I talked about the next thruster, NASA's Evolutionary Xenon Thruster. It was invented here at the Glenn Research Center. We partnered with Aerojet Rocketdyne to build it commercially. The Rollout Solar Arrays, which is the first time these have flown in deep space as well. In addition to the DART spacecraft, it carried a small CubeSat from the European Space Agency. It was called Lycia, was deployed before DART impacted, so it could actually image the impact and then later image the effect of the impact on the asteroid itself. This is a diagram that shows the orbit of Didymus and Dimorphos relative to the Earth. You can see at the closest point it just skims Earth orbit around the sun, goes out about almost 2.5 times the distance from the Earth to the sun. And that's what makes this impact interesting. We know the orbit of these asteroids by radar and optical tracking from Earth over long periods of time. That gives us an idea of its orbit. It gives us the size of these asteroids, but it doesn't give us a lot of detail. We know generally how big they are. We know generally how fast they're moving, but nothing really more than that. So as you launch from Earth, you have to target where these asteroids are going to be in their orbit, so your spacecraft will be there at the same time. You have to target the orbit of Dimorphos around Didymus to make sure it's in the right position when you arrive there, and then you have to back all this up in time to choose your launch window. And then you have to take into account that no launch vehicle performs perfectly, so you're going to have to do some course corrections. And then the fact that you're not going to actually know where your target is until an hour before you impact it. So what DART managed to do was hit a target 7 million miles from the Earth. After traveling over 100 million miles, it hit a target about 300 feet wide at a speed of 14,000 miles an hour after locking onto that target only an hour before the impact. And it hit that asteroid almost dead center. Some of the images from that Draco camera as we got closer and closer to the asteroid showed that, like many other asteroids we've looked at, this was not a solid rock. This was a pile of rubble, loosely held together by gravity. If you can imagine a ball of dirt being held loosely together by gravity, it's got some larger rocks in it, larger boulders. That is what this asteroid turned out to be. And as it got closer and closer and it kept returning images, and this is what we saw in one of the last images before the impact. Those boulders there are about the size of a human being, about 6 feet tall. But it looks like a pile of dirt. And the images on the right are from the Hubble and the Webb Space Telescopes that were looking at Dimorphos and Didymus, looking for this impact. And this is what was seen by both of those telescopes at the moment of impact. This is from an Earth-based camera in Chile that was focusing on that system. Of course, it can't separate the two asteroids as close as they are together. But you see the moment of impact and the debris, the ejecta, coming up from the surface of Dimorphos, the brightening of it as this cloud disperses and catches the sunlight. Now, this is looking from 7 million miles away and actually imaging from Earth that moment of impact. That CubeSat that rode along imaged the impact, and the image on the top left is that moment of impact from that Lycia CubeSat. And the cloud of debris that was thrown out by the impact was much larger, much brighter, and lasted much longer than anyone would have expected. In fact, the image on the right is from the Hubble Space Telescope taken 8 hours after the impact, showing the debris forming a comet-like tail from this asteroid. And after several weeks of tracking, we found that the mission was not just a success, but it was an overwhelming success. They were hoping to be able to alter the orbit of Dimorphos by perhaps a few minutes. Because of the nature of Dimorphos, the amount of ejecta thrown out by the impact, they actually slowed its orbit. They reduced the period of its orbit, which means it actually got faster. But they reduced the period of its orbit by over 30 minutes. So we know now that a kinetic impactor can target an asteroid that is in danger of hitting the Earth. And if it's far enough away from the Earth and we hit it with enough force, we can deflect its orbit and prevent that asteroid from impacting the Earth. Again, it sounds like something right out of science fiction, and it's actually science fact today. So with that, Don, we'll go back here to you.
So Jeff, what's next?
Well, what's next is doing a lot of tracking of the asteroid system, doing ground-based observations, optical and radar, to look at the effect of the impact of DART on Dimorphos, how much its orbit may continue to change, characterizing the ejecta that have been thrown out by the impact will give us more information about the makeup of the asteroid. And in 2 years, the European Space Agency will be launching a spacecraft with several other CubeSats into that system to get a better look at the asteroid and the effects of the impact of the DART spacecraft on it, to get, again, a close-up view of just what was done to the asteroid and what its makeup was. And it will just help us plan other missions and other ways of better protecting the Earth from potential asteroid impacts.
So we've gone, as you say, from science fiction to science fact. Jeff,
Yes.
I want to thank you very much for taking time out of your schedule to fill us in on this interesting mission. For the folks out there in TV land, please check out our website. The address, as always, is at the bottom of your screen. And coming up next with What's Up in the Night Sky is Stephen.
Thanks, Don. What's up in the night sky for December 2022? December is the month of the winter solstice, winter in the northern hemisphere. It's the shortest day in the northern hemisphere, the longest day of summer in the southern hemisphere. The month starts with a full moon on the 2nd, on the 7th, last quarter on the 16th, new moon on the 23rd, and first quarter on the 29th. Then we have all of the planets on December 31st, all in one go. Mercury and Venus go from Ophiuchus to Sagittarius. Mercury sets from about 25 minutes after sunset to an hour after sunset over the course of the month. Venus is like Mercury, just 10 minutes later. Mars is in Taurus and has opposition on the 8th. That means it'll be up all night. Jupiter is in Pisces and sets a couple of hours after midnight to midnight, and so there's always this 2-hour difference. Uranus is in Aries and sets 2 hours before sunrise to 4 hours before, and Neptune is in Aquarius and sets at about 1 a.m. to 11 a.m. over the course of the month. And that's what's up in the night sky for December 2022. Remember, we don't charge money for this show, but we may tax your brain.